Okay, I think we're connected. Now tell me what you guys are seeing here. Are you just seeing me? Okay, I'm going to switch us over to the screen for a little bit. And I'm going to ask you to turn off your mics, mute your mics so I don't get that feedback again. Excellent. And today we are finishing up chapter, whatever it is it chapter 1 we're in? Chapter 2. We're going to finish up chapter 2. We're going to talk about the engineering design process and the traits of a good engineer, and then we're done with the book for a little bit while we do a project this week. So let me see if I can get this to work right. Okay, camera. On. All right, let's see if we can make this work. Actually, we need to go back to here. All right, so today, it says in the book, chapter 2.10 through 2.12, we're going to study today, learn some things, hopefully. I'm going to amend that a little bit. We're going to cover section 9 as well, but only part of section 9. But anyway, we're going to cover section 9 as well because that is the engineering process. Now, the engineering process is something that we're going to deal with a lot when we're working on our project. But I do want to do an overview of it today. So, section 9 is they actually entitle it the engineering design method. And the engineering design method is similar to the scientific method. You've probably heard of the scientific method. Let's go take a look at something that would explain the scientific method to us. There are just literally thousands of different ways to think about it. We'll look it up on Google, of course. I want you to get used to finding things on Google, but not necessarily relying on the internet for everything. Because there's so much out there, we can see lots of different things, and so we're going to look at lots of different things. Let's take a look at this one here. View the image, right? So you've got this scientific method chart here, and it starts out with ask a question, do background research, construct a hypothesis, test with an experiment, analyze, is the hypothesis true or false, think and try again. Okay, that's decent. You've probably seen that before in some science class. It's not my favorite way to decide on what the scientific method. This is actually more what I would say is the scientific method. You make an observation first, because that's always what happens first in science. We don't necessarily ask a question first. Usually, we don't even know what the question might be. Usually, we just make an observation. For example, we always notice that when the clouds get dark and it gets a little bit windy, that it rains, right? And so we start asking a question. Well, why do the clouds have something to do with rain? And we form a hypothesis. So the rain comes from inside the clouds. Then we conduct an experiment, and we either accept our hypothesis because our experiment confirmed what we thought was correct, we confirmed our hypothesis, or we reject the hypothesis because our experiment showed that it wasn't true, or it gave us some doubt, or it didn't confirm it well enough for us. And quite honestly, in science, most often we go through the reject hypothesis to form a new hypothesis. But we can also ask a new question or make another observation, because during our experiment we may actually make a new observation and have to go back to the beginning. So you can go back to any part of the scientific process at the end of the process or near the end of the process. And like I said, there are literally just thousands of ways you can think about this. You can observe, state a problem, hypothesis, experimentation. There's just so many different ways you can go about talking about the scientific method. Here's a cyclical scientific method for us, right? Research, find a problem, make hypothesis, experiments, compile data, and that's got 8 steps instead of 5, so on and so forth. There's just so many ways, and it is very similar to the engineering design process. So what I'm going to do here is punch in the engineering design process, and let's take a look at what is different. What is different? You can notice here that there are charts here that are cycles, similar to the one that we saw with the scientific process. Here's one that comes in steps. This one's from MIT, so maybe it's a good idea to look at this one since MIT is one of the best engineering schools in the nation. We have construction planning, final design, preliminary design, feasibility design, and they say that these are design cycles, and that this thing is a loop that keeps going and it goes from one thing to the next. So maybe a little bit difficult to understand how that one works, but it's a decent representation. Oh, come on, get out of my way. Here's one that's probably a good one here. Here we start up here at the top with an engineering design problem, right? And we go down here to identify DFXs and metrics. Essentially here what we're trying to decide on all the things that can be measured and tracked here. And then we divide the problem into sub-problems. We identify candidate solutions, possible solutions, all the possible ways of accomplishing the desired function or task. Analyze similar design solutions in other fields. So we're essentially researching what has been done already. Then we go down here to evaluate candidate solutions. We decide which ones are the best, compare them using measurements, and then we create matrices to compare things piece by piece or side by side or whatever else. Then we unite optimal candidate solutions into one design solution. So we take all these ideas that we had and we put them into an actual final design. And then we evaluate the design solution based on metrics. So we might make our design, or we might build our design, or we might build a model of it or something. And then we measure its performance. We figure out if it works the way we thought. If it does, then we might actually be done, but most likely we're going to have to go back and maybe play around with it a little bit. So we can go through this cycle of finding solutions to problems, evaluating solutions, building the design, and then testing the design. So that's not a bad one. Just like the scientific design though, which I keep going back to far, there are lots of different ways to think about this. Here's another one that's similar to that last one. Here's another one that goes through some kind of strange chart thing here where we have some event, and then we have a function information. I mean, this is kind of a goofy one that you have to understand a lot about organizational charts to understand. Maybe we go to this one here. Let's try this one. This one's designed specifically for electronics, but it's also a cycle. You can see arrows going everywhere. So the point I'm trying to make here is that there's just infinite number of ways to think about the engineering design process. And this is actually one that I want to look at, because this one is probably one of the simplest types of charts to look at for what we're trying to figure out here. Let me see if I can zoom in on this a little bit. It's not so easy on this computer to zoom in on things, apparently. So we'll zoom in with the camera. Zoomify. Kind of helps. Woo. Zoom some more. Okay, so here we have the engineering design process in 5 simple steps and a whole bunch of arrows. We start off with identifying the problem. With engineering, you're always going to be solving some kind of problem, some kind of need that needs to be filled, some kind of issue that needs to be resolved, some kind of function that needs to be accomplished, something that needs to be done. Whatever it is, you're going to be identifying the problem to start off with. Once you have identified the problem, and make sure that that's very specific and very complete. You don't just need to say, well, we need to move this box from here to North flat, or from here to McCook, or whatever. That's not very specific. We need very specific things. We need to know maybe the size of the box, the weight of the box, what's in the box, is it fragile, is it not, and what are we going to use to move it with? Maybe we need to move it on a cart, maybe we need to move it through the air, maybe we need to move it without moving it too fast, or move it without turning the box on its end or something, keep it in a particular orientation. We need to identify the problem with specifics, okay? We need to have specific parameters that we're trying to meet in this problem. Then we're going to look for relevant information. This is kind of a research process. We're going to look for possible solutions, people that have done this before. We're going to look up information about the problem. Maybe we're looking up information about the box that we're moving or the item that we're moving. We're going to gather all the relevant information, do a lot of research, so that we're ready to go when we start designing for real. This is all part of the process, but we haven't really started designing yet. We're gathering information, and then sometimes while we're gathering information, however, we find that we need to identify the problem better. Sometimes we find out that the cardboard box cannot be moved in such a way that we're trying to move it, so we need to go back to identifying the problem. Maybe we need a new box. So that becomes part of our new problem, right? So that's why they have this little orange arrow that goes from relevant information back up to identifying the problem. Then, once we have gathered the relevant information and we've completed identifying the problem, then we move on to conceptualization. Go down to this conceptualization box here, which is essentially where we start the actual design. We look at past designs and other people that are in the field or maybe in similar fields. We look at what has been tried in the past and has failed. We look at anything that might be similar to it. We look at the materials that we're going to use. We maybe decide that we're going to try this kind of a design because it was almost successful in the past, but we're going to change it in a particular way. It's going to include drawings. It's going to include models. It's going to include mathematics. We're going to be doing geometry. We're going to be calculating forces. We're going to be calculating all kinds of things here. This is where a lot of the design is done, right here in the conceptualization. We're coming up with a concept for our problem that's going to solve our problem. And that concept has to be, again, very specific. We can't just say, well, we're going to build a vehicle to move this package. It needs to be what kind of vehicle, what's going to make the vehicle go. Is it going to run on wheels, or is it going to run on tracks, or is it going to be a magnet levitation vehicle, or are we going to shoot the package through the air with a catapult, or whatever. And then we need to design those things. We actually need to draw them out. What materials we're going to use, what's the size are we going to be, how is it going to work in this way and that way, situations. We're going to design it the best we can so that we think that there's nothing left to design. It is complete. And maybe even we're going to prototype it. So maybe we're even going to build one. In some cases that is possible, in other cases it's not. But we might even build it at that point. If we build it or if we don't build it, doesn't really matter. When we're finished conceptualizing, we're going to evaluate it and analyze it. We either evaluate it in real life using the prototype or the thing that we actually built, or we're going to evaluate it some other way so that we can evaluate it not physically but mentally in some way. And so in the case of computers, you can actually build models that will test a digital prototype or a digital model of these designs. But once you start testing and you've built this thing and you're testing it, you're going to find out that some things work like you thought they would, others don't, and you're going to take data. You're going to take information based on these tests, and you're going to decide what needs to be changed, what is good. Maybe something is overbuilt, maybe something was a complete failure, whatever. You're going to evaluate your design, and you're going to analyze your design. When you evaluate and analyzing your design, the most likely place that you're going to go is either back to conceptualization, where you're going to build or you're going to come up with a new concept to fix the problems. You might go back to this information part because you figured out that you're missing something. You need to go study some more and get some more information. And if you go back to that information spot, you're going to have to go back to conceptualization. And you might even have to go back to identifying a new problem. So if you go back 2 steps, you might be in trouble. You might be starting over with your drawing board, right? Or Or you can go all the way back to the beginning. When you've analyzed your solution, you find out, well, this thing works, but it doesn't solve our problem. And it turns out maybe our problem isn't the problem we thought we had. And so you might have to go all the way back to the beginning. And it doesn't necessarily mean that it was a bad design. It just means that if the beginning of the process maybe didn't reach the right conclusions or the right problems or gather the right information or anything else. And it happens to the best of engineers. Once you have completed the evaluation and analysis section, and you maybe have gone back and gone through this cycle a couple of times more, and you're done here now and you go on to implementation, that is the end of the cycle. You have essentially designed something that works, it solves the problem you were looking for, there's nothing missing in the design that is important necessarily, and you go on to implementation. The implementation doesn't necessarily mean it's done, it's just that the design is done. Implementation may involve designing a factory that can build this thing. It may involve opening a factory so they can use your techniques in the factory. It may involve installing a piece of equipment that you've just designed in a particular system somewhere. It may involve selling your design to some other company. I'm actually involved in I'm involved in a project right now where somebody in this community who has an interest in outdoor hiking, camping, hunting, stuff like this came to me with this idea that he has for a camping device. And it's a really good idea. And he had already identified the problem. And when he brought me this device, the first thing I started doing is I opened up my computer and started looking at other companies who have maybe tried to do similar things, other designs, other uses for this thing. We started putting together a bank of information that we could use to make a design. And it was a little bit frustrating for him because he wasn't aware of this he wasn't very familiar with this process, because he wanted to immediately go to conceptualization. I want to draw a picture of this. I want to design this part. I want to design this thing here and get it out there, in the world. But what I said to him is we got to gather the information, and then we can start to think about designing. So we never even got to any design stage. We just talked about it, and we just gathered lots of information. And I sent him packing. Essentially, I sent him away and said, go off and start organizing this information into some kind of order so that we can make use of it, and then come back and we'll start conceptualizing. Then once we conceptualize, then we can test, and then we can implement. And it's something that may, be very successful, could make him thousands of dollars, I think, maybe even more. But you can't just jump to the design part because you're guaranteed to waste time and make mistakes. So the implementation can involve so many things, but it takes a while to get there. It takes a while to get there. Another thing that implementation often involves is safety. Safety things, and also your responsibility as an engineer towards the community or towards the world or towards whatever. You have a responsibility as an engineer to do the right thing. You don't want to design something that's going to make you a ton of money and solve all kinds of problems if it causes all kinds of problems as well. You want to think that through and make a decision that is based on some kind of moral direction. So, the engineering design process, that's as good a chart as I have ever seen at explaining that process. And like I said, there are just lots and lots more here, and they're all very similar, but some of them are going to have a lot more detail, some of them are going to be a little bit harder to understand or follow, but still, they're all very similar in what they're trying to convey to us. So what I like to do now is go to the book and show you the one that's in the book. Again, it is very similar, but it's not exactly the same, and it doesn't have a nice graphical design to it. So let me see if I can get into this, show you this picture. I can't seem to, there it is. We'll zoom in on it. This is on page 39, and it's just a list. It's a very simple list here. The first thing on the list is to identify and define the problem. So very similar to what we just talked about. They include a step here that is sometimes necessary, but sometimes not. And the step is to assemble a design team. In most engineering fields today, it is necessary to assemble a design team because most of the time you're going to be dealing with lots of different fields and you don't want to be the one that's designing everything. So assemble a design team is an important step, although sometimes it's not always necessary. Sometimes it's just a single person doing the design process. Number 3 is to identify constraints and criteria for success. Right? And so that is actually part of the gathering information and also kind of defining the problem. So these two things are, step 1 and step 3 in this process kind of belong to 2 different sections on the other design process, but it's still a nice way to say it. Number 4 is search for solutions. And that, of course, would be in the gathering information. You're going to start looking out there at what has been done, what can be done, what are the possibilities. And then you analyze each potential solution, again, part of the gathering information, but also kind of part of the putting together a design part. Choosing the best solution and documenting the solution are also part of that design that design conceptualization part. You're putting together your solution, you're starting to draw pictures of it, you're starting to include dimensions, materials, how you're going to do this, how you're going to do that, what you're going to use, whatever. And then number 8 is to communicate the solution to management, right? Again, if you're working in the engineering fields today, you're more than likely going to have to do that. But it's not always the case. Not all engineers work for somebody. And then to construct the solution, of course, that is implementation. That is, you're bringing it from just a design into an actual thing, and you're going to start to verify and test it, verify and evaluate the performance of the solution. The thing I do not like about this list is that it doesn't show it as a cycle. It doesn't show the engineering design method as a cycle. However, in chapter 5 of this book, they cover it in much greater detail. So the entire chapter 5, is about this cycle, and this is on page 119. We'll get to this later in the class, but I am going to look at it right now and really quick. So notice that it's very similar to some of the ones we saw online. Once again, let's see if I can get my screen to look at that better. There we go. So it's got a box up here at the start, and it goes on through each of these things, and then all of a sudden there's arrows going everywhere. So you can follow the chart around in different directions, and this is much more like a cycle, those 10 steps that they give us in chapter 1. And why do we show you this right away? Because we're going to have a design project starting on Wednesday, and I will give you the information for that project today. We'll look at it today, and I'll post it and email it and do all that stuff so that you can have it. But I want you to try to follow this process somewhat. I want you to try to follow it at least a little bit. We'll start off with the beginning parts of the process, which are, of course, to define the problem and essentially gather information. But I want you to try to use as many steps as you can. And we have a worksheet to help you to follow those steps and help you to experience what it's like to be an engineer using this design process. So that is section 2.9 out of the book. 2.10, 2.11, and 2.12 in the book essentially essentially are going to talk about what it takes to be a good engineer. The traits of a successful engineer, right? And that's 2.10, the traits of a successful engineer. 2.11 is creativity, right? And 2.12 are the traits of a creative engineer. Let's take a look. I want to look at the homework that we're doing for today. The homework for today is, let's see, what is it? Numbers 9 and 11, chapter 2, homework problems 9 and 11. Number 9 says to look around the room you are in and identify how engineers were involved in the creation of 10 things. So it's not just to identify 10 things that engineers were involved in, it's to identify how they were involved in it. And then number 11 rather, is to write a one-page report on the relationship between engineering and business based upon the following examples. So you need to go out and you need to study James Watt and Matthew Boulton, Nikola Tesla and George Westinghouse, Wilbur and Orville Wright, and Glenn Curtiss. Okay? So there's those 3 relationships, you need to study them, and then you need to write a one-page report, or was it half-page, whatever it was, on those relationships. And why do we want you to do that? Because we want you to realize that engineering is not just about building things, it's not just about designing things, it's not just about playing around. That is a big part of it, and that's fun. But you have specific things that got to get done, right? And engineers have to have a lot of skills and a lot of abilities, and they don't have to have them when they start, studying to be an engineer. But by the time you're done, you have to have gained these skills. So let's go into section 2.10 and talk about some of these traits of a successful engineer. I'm going to go ahead and write them up on the board here as we talk about them. So I need to readjust my camera so you can see my whiteboard. Okay. And zoom out. Okay, so hopefully I can write big enough so that you can see what I'm writing on. And this list, it's a long list actually. And some of these things you'll just think, oh, of course engineers have to have common sense. That makes sense, But the problem is that common sense is not all that common. It's actually pretty uncommon. We should call it uncommon sense. But there are a lot of things that you're not going to think of. One of the first things that they mention here is, that's not going to work. Move this stupid chain out of the way. One of the first things that's listed is interpersonal skills. Interpersonal skills. Essentially, you need to have some ability to communicate with others, to work well with others, to be social. But why? Why does it matter? Well, let's take a look. I'm going to do a search here really quick for an engineering paper. So almost any time people do something in engineering, they write a paper. Let's actually do an engineering article, maybe. Paper brought up the wrong thing. We're going to bring up an engineering article here. So here we have the 2000 TDI engine rebuild. That looks like car engineering of some kind. Let's look at, let's see if we can find something here that's really interesting. HPAC engineering. So let's view this image here. I'm trying to find one that I can actually see. Let me move my camera again so you guys can see it. Wrong direction. Okay. So that, I need to find a paper that I can read. So we'll see if we can here. Here's one that you can almost see, not really well. Portable cooling equipment and applications. So this is essentially a portable air conditioner of some kind. And you can't really see here, but it looks like there's at least 1, 2, 3, maybe 4 three or maybe four people who wrote this article together. And what that means is going through the engineering process, there are at least 3 or 4 engineers working on the process, working on this project, okay? It is very rare, goodness, why can't I find my, there we go. It is very rare to have fewer than 3 or 4 engineers working together on a project. And so you have to be able to get along with people. You have to have experience working with other people. There are plenty of papers where you're working with engineers all the way across the world. And a good example of this is actually, this picture right here is actually a good example of this. I believe that this is actually a picture of one of the biggest scientific projects in the world today. Let's see if we can find that picture again. Where did it go? Oh. There's my camera. Now let's find the right source. So here's a picture of a detector that's being used in what is called the Large Hadron Collider over in Europe. It's a $25 billion project. This thing is several stories high, and they have this particle beam going down the center of this thing. There are engineers all over the world that work on this project, and some of them have never even been to Switzerland, where this project is. So all their work is done remotely. They're sending emails, they're sending letters, they're doing video conferences. They're traveling all over the place. They're meeting with people that speak different languages and don't speak English with them. So they're trying to communicate with people speaking German or whatever else. And yet the project is successful. They have accomplished what they went out to accomplish, and they accomplished it fairly quickly. They've discovered a new particle called the Higgs boson. And the Higgs boson is essentially the particle that accounts for mass. It explains why mass exists. It's a really important project scientifically. And yet thousands of people had to work together to get it done. So interpersonal skills are absolutely essential. Not just because you're having to deal with other scientists and other engineers, but your money is coming from businessmen. And you have to be able to deal with them as well. You have to be able to come across as a nice guy, come across as somebody that's understandable, that's going to do a good job. You have to be able to work with just about anybody. So switching back and forth between inputs is a real pain in the neck. But I guess we'll do it anyway. Camera, we'll just go back over to my whiteboard. Like that. Okay. So interpersonal skills, quite important. Leadership skills, right? We gotta have leadership skills. I think that one's fairly obvious. Why we need to have leadership skills when we're dealing with engineering, because somebody's got to take charge, somebody's got to work hard, everybody's got to be able to work on their own, but also be able to work underneath somebody that's leading the group, so you have to be able to both lead and be led. So those things are obvious, but one thing that may not be so obvious is that engineers are often looked to in other situations as leaders because of their abilities that they've gained as engineers. And so in your community, in your kids' schools, in other places like that, you are probably going to be a leader, and that's important because we need engineers out there that are going to encourage other people to go into engineering. So I spend a lot of my time in the community going out to schools, doing science shows, encouraging kids and encouraging teachers to build up engineers, future engineers. And all engineers should do that. It's very important. I actually skipped one. It's kind of funny that I skipped this one. Communication skills, right? Gotta have communication skills. You're going to have to speak with other engineers, you're going to have to present to other engineers, you're going to have to write. All engineers write, and they write a lot. I would guess that an average engineer spends at least 20 to 25% of their day writing. Either writing communications with other people, emails, letters, memos, things like this, but also they end up writing papers, they write reports, they write technical manuals. One of the first job I ever had engineering, the first assignment I got was to write an instruction manual. Actually, the first assignment that I got was to write the final report for the project that they put me on. So I had just started and they were already writing the final report and they assigned me to do it. Well, it was a really good experience. I spent most of my day researching, looking at what they were doing, asking questions, gathering information, and writing and writing and writing and writing. Then my last project, the last thing I did in that job a year and a half later, was to write a technical manual. I wrote an instruction manual for this thing that we had designed during that time. And that technical manual has been revised many times since, but they're still using some of the original stuff. So writing is certainly important, but all communication skills are important. Competence, knowledge, understanding. You cannot be an engineer if you are not competent. If you do not have the schooling, if you didn't work hard in school, if you didn't figure the things out that you were supposed to figure out while you were in school, if you didn't use the experiences that you had in school to learn more, and if you didn't go out in the workplace and learn more. Engineers are competent above all else. They are competent, competent, competent. They work hard, they learn well, and they keep learning all the time. There's never an end to learning in the engineering field. There shouldn't be an end to learning in any field, but unfortunately it's not true. If you stop learning in engineering, you will get fired, you will not be an engineer anymore. So you must be competent. It involves everything from schooling for the rest of the life. Logical thinking. This one's also important, but it is different than competence. Logical thinking is absolutely essential. You must be able to look at a situation and gather information and figure out what must happen. What will happen next? What is the logical result, right? What are the illogical results? You don't want to go off on tangents and waste time doing things that don't make sense. Quantitative thinking is next. So you have to be able to think using numbers, using math. And that's why we teach put so many math class, quantitative. There we go. Quantitative thinking. So math skills are essential. Follow through. So you have to be able to endure. It's going to take a long time to get your degree. It's going to take a long time to get experience. You have to have patience. You have to have persistence. You have to be able to follow through. Continuing education, I already mentioned that. You're going to do lots and lots of learning as an educator. Maintaining a professional library. So, I would say that every book that you get in engineering, mathematics, or science, from calculus on, you should keep. People say, well, why? We have the internet. Well, because you should keep the book that you learned in. You took notes in it, you highlighted things in it, you should keep it, and it should be your library from then on. And you will use them, I promise it. And you will also collect other books that are not textbooks. And you should keep those. And you should have a professional library. Not only does it work as a knowledge base and a resource for you, but also for others, people that want to learn. Dependability. Engineers work on deadlines. Engineers work under supervision and under the authority of others. And if they can't depend on you, you're going to have a problem. There's a lot of things to do with that. So what this relates to now is school. If you're the kind of person that puts off your homework to the last second, that turns in things late and asks for, special deadlines from the teacher, or goes back to a teacher and says, I forgot this, will you let me turn it in late? You need to break those habits right now. Because that will work, that will get you through school. You can even have great grades through school. But if you do that with an employer, you'll lose your job. First time. You have to break those habits early, because it will not automatically change once you're getting a paycheck to be as an engineer. You won't automatically do things on time. If you're not dependable as a part of your nature, you need to become dependable. Honesty. If you don't know something, admit it. Honesty. I can spell. If you did something wrong, admit it. Because if you do something wrong and you lie about it and they find out otherwise, they will be angry. You will probably get fired. Getting fired from a job is not like getting fired from a job as a teenager. Get fired from an engineering job, you will not get another engineering job probably for the rest of your life. Okay, if you get fired for doing something wrong, you will probably have to go and do something else with the rest of your life. And it's not something you want to deal with. So honesty. Practice being honest now. Don't tell your teachers, well, I didn't do my homework because I had to do. Tell your teachers, I didn't do my homework because I forgot. And I won't do it that way again. Don't lie to teachers. Don't lie to your classmates. Don't lie to your parents. Be honest in everything that you do so that you don't have to break that habit later in life. Here's a big one. This is one that I am not very good at. Organization. The more organized engineers have a tendency to get paid better, because their employers look at them and say, you could help others in a project. When they come into a room that's clean and orderly, they think they'll be able to make others do the right thing and get the things done. When they come into a messy office, they think you can't even clean your own office. You'll never be able to manage a team. You'll never be able to get things done if you can't even clean your room. And so they'll just leave you designing some hinge while the guy next door, who has maybe less experience and maybe even less skill, is managing the team and getting paid twice as much. Organization is important. Learn it now, be able to use it later. Common sense. Again, like I said, it's not very common. So learn to use it. Pay attention to people who are older and more experienced than you. Don't assume you're always right. Common sense. Think things through. Think of all the possible implications of your actions. Think of everything that you possibly can. Talk to others, get their input, and use common sense to make decisions. Now we get into some that are a little bit maybe less obvious. The first one being curiosity. The next one being, the last one being, creativity. And they also include involvement in the community, which I talked about before. So I'll put that one last. But I'm going to put curiosity and creativity together. So here's involvement in the community. But curiosity and creativity are things that engineers are often accused of not having. Why? Because people think of engineers as these guys with pocket protectors and thick glasses. But in truth, there are very few people less curious and less creative than engineers, or more creative and more curious, rather. There are very few people that can beat an engineer for curiosity and creativity. Very few people will look at everything around them and want to take it apart because they're curious and how it works and what it's made of. But engineers have a tendency to enjoy that. And if that intrigues you, do it. If that intrigues you, do it. Take an old cell phone apart. See what's inside. Try to make it work again. Try to do something else. You have to be careful with that. Some electronics are dangerous. Some other objects can be dangerous. But curiosity is an essential part of being an engineer. And creativity. 99% of the creative acts of mankind were done by engineers, not by artists, not by musicians, by engineers. Everything from the wheel or the lever or whatever, the first engineered, domesticated all trees all the way until the latest, greatest stuff going on today, all about engineering. And there's so much. Creativity is absolutely important. And not only that, but if you go to a town like my hometown that has 15,000 engineers in it, I think the last count, my town had 15,000 engineers and only has about 90,000 people or 80,000 people in it. That's a lot of engineers in one place. Only a couple of towns in the whole world that are that concentrated with engineers. If you go to a town like that, you'll find that a town with 80,000 people can support a full orchestra because so many of those engineers are actually musicians as well. A town like that can support an art museum that's really quite good because so many of those engineers are actually artists as well. That the creative part of engineering is not just about mechanical stuff or electrical stuff or whatever. It actually spills over into many other fields. And so you'll find some very interesting communities when you have engineers in them. Santa Fe is another similar community that has a lot of engineers near it and in it, and it's a very artistic community. There's a lot of art going on in Santa Fe, New Mexico. So, anyway, so those are all the, those not all the traits, but those are some of the major traits of engineers and what makes engineers who they are. They spend a whole section on creativity in 2.11, and they have these charts that kind of show how they use some of these traits, these organizational traits and everything else in specific in specific ways. So they have these facts by organized thinkers, disorganized thinkers, creative thinkers, that really engineers are actually kind of a combination of lots of different types of thinking. So also, let's see, section 12, they talk about the traits of a creative engineer. So sections 11 and 12 are mostly about creativity. And I'm not going to go into great details in those, but they are important. They are quite important. And we will get to it. We will get to more of that stuff as we go through the engineering process more. What I want you to take away from today is that there is a process that we need to follow, at least to some degree, of engineering design. And that process requires all these different traits of an engineer. The process requires organization, it requires communication, it requires competence, it requires creativity, it requires all kinds of different things. And we're going to spend essentially the rest of this class going through the design process and trying to develop and explore these traits of engineers so that we become the kind of people that will be engineers. So let's take a look really quick. We've got just a couple minutes left here. Let's take a look really quick at our project that I'm going to be sending out to you. Let's see if, there we go. So, figure out where it is here really quick. Put it up on the screen for you guys to look at. Okay. Courses. All right, so the project is the bridge building project. Let's see if we can get it in here. Well, the bridge guide is our... So what we're going to do is we're going to follow this awesome bridges activity guide, right? And this is actually designed to be used with the materials that I've sent you, so you can see the wood beams and everything else. And they're going to kind of step us through the design process a little bit, the beginning of it anyway. And they talk about the supplies that you'll need. Now, some of the supplies I supplied I gave to you, some of them I didn't. For example, I didn't provide glue, and I didn't provide steel wire. So if you can't get steel wire, just tell me and we'll try to get you some. I forgot the steel wire. And the tools I didn't provide, but I'm hoping that you can use tools at your school or at your home to do that. Please be careful if you're using power tools not to cut a finger off, for example. Here they talk about the engineering design process. Again, another representation of that process, but a good thing to look at. And then they start talking about different tools that you can use. They actually have West Point Bridge Designer. You can actually get a bridge designer online and use it to design your bridge. And they talk about the problem statement and the design brief and the materials you're going to use and their strengths and their strengths and weaknesses. And they're going to talk about mapping out a design on a paper. They're essentially stepping you through this process, and you're going to go through the process and keep track of everything you do in this form. So when they talk about building a drawing, putting together a drawing, and deciding what kind of bridge it's going to be, you're going to put together a drawing. And all the stuff that you need is available here. They'll tell you where to get it online, or you can call me and I can help you with that. But they're essentially stepping you through the design process. And they have the problem at the beginning as well. Where's the problem? Here's page 1. The problem statement is we're going to, I guess it doesn't actually say it here. Oh, here it is. So the problem statement here, what is your problem? Design brief, we're going to build a bridge that meets the following design constraints. And that's something that I'm going to tell you. So we're going to pick a distance, and I think the distance will be 2 feet. And you're going to build a bridge that will go 2 feet between two desks or two tables, 2 feet long, and will support like a 2-pound weight. So it's going to be 2 feet, 2 pounds, right? So that's pretty simple, and I'll include that when I send this out to you. So you've got lots of stuff to work with, lots of tools that are going to help you through this process. We have essentially Wednesday and Friday to do this, and you can ask me questions. I may answer your questions, but I may answer them with a question, and I may answer them with an assignment for you to go out and do, right? But I also may just answer your questions. I'm not going to do the work for you, though. So I will send this out to you so that you can have it, and on Wednesday you're going to come to class and ready to start the process. You're doing this individually, so you should each have your individual building kits, and you don't want to use all the parts up because we have more than one project to do. So you don't want to just start building things and see if they work. You want to design it on paper first. So that's what we have for coming up on Wednesday. You also do have homework tonight from the end of chapter 2. Make sure you get that done, and we are done for today. So have a good day. Do you have any questions there in Stapleton before I sign off? All right, have a good one.